Imagine a scenario where you're trapped in a cave, or more like dropped in a cave, with a dragon. Highly aggressive and blazing, flaming, raging hot dragons. Not only so, but every 10 minutes, the dragon makes a copy of itself, which 10 minutes later also makes a copy of itself, and 10 minutes later makes a copy of itself. So here's the question. How long do you have until a cave is populated with 1,000 of them? We can use a table to represent the duration you stay in a cave and a number of dragons. At 0 minutes, when you just entered the cave, there would be just one dragon. 10 minutes later, 2 dragons. 20 minutes later, 4 dragons. And 30 minutes later, there will be 8 dragons. Notice that as you go down the rows, the left column has 10 added, while the right column is multiplied by 2. To find the number of minutes for 1,000 dragons, we can keep expanding this table, or we can express these numbers in terms of the variable n. Let's define n as the number of times dragons have duplicated. At the nth time the dragon duplicates, the number of minutes you stayed in there would be 10n, and the number of dragons existing would be 2 to the power of n. This is an exponent, which refers to the number of times a number is multiplied by itself. In this case, 2 is the base and n is the exponent. When n is 1, 2 to the power of 1 means 2 is multiplied by itself once, so there are 2 dragons, and as the value of n increases, the number of times 2 is multiplied by itself increases accordingly. Following this rule, when n is 0, so when a dragon's population is 2 to the power of 0, 2 is multiplied 0 times, so the dragon's population is 1. Now that we know about exponents, we can find the answer to the question easily. The dragon population, 2 to the power of n, equals to 1,000. To find n, we would need to use logarithms, which we will explain later, but right now just know that n here is roughly 10. So around 1 hour and 40 minutes before you're stuck with 1,000 fire-breathing dragons. Now you realize these dragons are actually very friendly. You become great friends with them, and they decide to give you red pockets at Chinese New Year. The dragons are scattered around the forest, waiting for you to find them. You know they are stationed 1 km apart from one another. Each hold red pockets with $1,024, and are organized so that the number of new dragons you meet are always the same as the total number of dragons you've previously met. So every 1 km you double your money. How far would you need to walk to become a millionaire? To break this down, for the first km you walk, you would meet 1 dragon, which gives you 2 to the power of 10 times $1. For the next km, you would meet 2 dragons, which gives you 2 to the power of 10 times $2. For 3 km, you would meet 4 dragons, which gives you 2 to the power of 10 times $4. For 4 km you walk, you would meet 8 dragons, which gives you 2 to the power of 10 times $8. So for every n km you walk, you would meet 2 to the power of n minus 1 dragons, and it would give you 2 to the power of 10 times 2 to the power of n minus $1. If you apply the product rule of exponents, where a to the power of m times a to the power of n equals to a to the power of m plus n, 2 to the power of 10 times 2 to the power of n minus 1 equals to 2 to the power of 9 plus n, which equals to 1 million. And applying the logarithms rule, log 2 1 million equals to 9 plus n. This gives bracket log 2 1 million bracket minus 9 equals to n. This makes n roughly 10.9 km. By the way, there are also other exponent laws. The first one is the product rule, which is a to the power of m times a to the power of n equals to a to the power of n plus n. There is also a quotient rule, which is the opposite of this, giving us a to the power of m divided by a to the power of n equals to a to the power of m minus n. Next, we have the power of the power rule, where bracket a to the power of m bracket to the power of n equals a to the power of m times n. Another one would be power of the product rule, where bracket a times b to the power of m equals to a to the power of m times b to the power of m. The opposite of this would be power of a quotient rule, where bracket a divided by b bracket to the power of m equals to a to the power of m divided by b to the power of m. The last 3 that we'll cover is the zero exponent rule, where a to the power of 0 equals to 1. A negative exponent rule, where a to the power of negative m equals to 1 over a to the power of m. Lastly, we have the fractional exponent rule, where a to the power of m divided by n equals to root n a to the power of m. We can also create exponential graphs. This is a graph of y equals 2 to the power of x, a representation of our dragon population. From looking at the graph, you can observe that there is a y-intercept at the coordinates 0, 1. As the value of x becomes smaller and becomes negative, the graph starts to approach an asymptote, which is a line that the graph forever approaches but never actually reach. In this case, this is when y equals 0. On the other hand, as the value of x increases, the graph starts to grow exponentially, where it approaches infinity. The general formula for exponential functions is y equals a times b to the power of x, where a is the y-intercept, which means that as a increases, the value of the y-intercept increases accordingly, and vice versa for if the value of a is negative, and b is the growth or decay factor that influences the shape of the curve. If b increases, the curve becomes steeper, and when b equals to 1, it forms a flat line. When b is between 0 and 1, the graph curves towards the other side. b can also not be negative, otherwise it would lead to non-real values. And now that we know all about exponents, we can talk about logarithms. Logarithms are kind of like the opposite of exponents. It places the exponent on one side and the base and value on the other. If exponents are written as a to the power of c equals to b, logarithms can represent this by writing log base a bracket b bracket equals to c. For example, looking at a solution to the dragon population problem, we have the equation 2 to the power of n equals to 1000. To find the value of n, we use logs and write that equation as log base 2 bracket 1000 equals to n. Then simply key this into your calculator to find 9.96, which is roughly 10. Graphing logarithm functions would look like this. Notice that there is an x-intercept at the coordinates 1, 0, and an asymptote at x equals 0 where the graph approaches the line but never touches it. As the value of x increases, the graph starts to approach infinity. Notice that this is actually the inverse of the exponential function we've seen before. An inverse function is where the x and y values are swapped in the original function, and the graph of this inverse function is a reflection of the original across the line y equals to x. Let's talk about logarithm rules. Log of 1 rule is where log b1 equals to 0. There's also another rule where log of the same number as base, log bb equals to 1. A product rule is where log b bracket m times n bracket equals to log bm plus log bn. The opposite of this would be the quotient rule, where log b bracket m divided by n bracket equals to log bm minus log bn. Another one would be power rule, where log bm to the power of n equals to n log bm. There's also a change of base rule, where log ab equals to log cb over log ca, or this can be written as log ab times log ca equals to log cb. There's also equality rule, where log ba equals to log bc means that a equals to c. The number raised to log rule is where b to the power of log bx equals to x. Some other rules would be where log b to the power of n, a to the power of m equals to m divided by n log ba. There's also another one where negative log ba equals to log b 1 over a, which alternatively could be written as log 1 over ba. Here are the proofs for 4 of the logarithm rules: the product rule, quotient rule, power rule, and change of the base rule. Feel free to pause the video to see the full proof. That's it for today's video. We hope you enjoyed.